Thank you very much. And let me thank the organizer for this wonderful conference and inviting me to speak. Now, my talk is Quasivoid, a quasi-particle approach for the dynamics of structural glass. I am Chi-Han Lam from Hong Kong Polytechnic University. A glass is a state of matter with a disordered structure. So we consider in a more generic approach. So example we will look at include usual window glass, glassy polymer, metallic glass, and so on and so forth. Now, as temperature decreases, the viscosity of a glass or the supercooled liquid increases. When the viscosity reaches a really high value, which is not infinity, then this is defined as the glass transition. And the temperature which it occurs is called the glass transition temperature. There are many fundamental open questions of glass. I think the most important question is whether there is a sharp phase transition associated with glass transition, or is it just a smooth crossover? And there are competing theories trying to explain all the open questions or most of the open questions, including our own theory, which is closely related to an earlier facilitation picture. This is some small-scale molecular dynamic simulation of glassy polymer. So in this polymer melt, we can single out a polymer, look at what happens, and then we can further single out one of the monomer, that is one particle, like this. At very low temperature, the motion consists of vibration and hop. So we can look at it more carefully or more clearly from the trajectory of its center. And so we see that it vibrates at some metastable position, and then all of a sudden, it has just hopped to another metastable position. And it is a time-colored trajectory. So the color is assigned according to when it happens. So we can further do some moving window time averaging to get coarse-grained trajectory so that vibration is mostly suppressed and the hopping event is highlighted by this long line segment. This is called a time-colored coarse-grained trajectory. And from the same simulation, we highlight 3 of the particles which hopped together, and we can see them clearly from the coarse-grained trajectory. And the same color of this long segment representing the hop means that they hop at the same time. And each particle invades the previous position of the neighboring particles. And this is something called a string-like motion, which is very important to our observation. Now, I want to present our colloidal glass experiments, which is widely believed to be closely related to generic glass. So we take micron size PMMA spheres with bimodal diameter distribution so that they will not easily crystallize. We put it on a substrate and look at it using optical microscope to form a closed packed 2D amorphous system. And it is immersed in water, so they carry out Brownian motion. And then we show its dynamics by coarse-grained trajectory. So, and we look at very high packing fraction to get the generic glassy phenomenon. At shorter time, it is mostly vibration. And then when we look at longer time, we see that many particles move like that in the form of string-like motion. And remember, different color represent the string-like motions occurs at different time. So for example, this string-like motion consists of 3 particles moving around, moving in one direction. And each red dot here represents the initial position of a particle. So you can see that many particles has not moved, and some particle has conducted string-like motion. At even longer time, there are more string-like motions, but some particles still has not moved. So these results are for very deep supercooling at at high density. So we observe that it is mostly string-like motion. And we believe it is a simple system or simpler system compared if you would do a moderate supercooling when you have both string-like motion and also some liquid-like collective flow behavior. Now, some of the trajectory still looks complicated. So in this experimental result of very high density and long time, we can split up this trajectory into 8 time consecutive sub-trajectories and then look at its detailed motion. So we see string-like motion, actually all of them are simple string-like motion. And then when they superimposed in the longer time trajectory, it looks complicated, but it is just string-like motions. So we conclude that string-like motions dominate glassy dynamics, even at very deep supercooling. And then what causes string-like motion? Now, one important puzzle is that for highly or closely packed system, there is no large void, no large empty space. So in a string-like motion, particle really displaced by roughly the particle diameter. So how can the first particle in a string-like motion, that is in the string tail, be able to hop if there is no large space provided to it? Our observation is that there is no single large void, but there are a few, smaller free volume fragments. And these free volume fragments are now allow the neighboring particles to be squeezed away so that this particle can squeeze in. But everything happens at the same time. So at no time we will see a large void here. But because of these volume fragments, free volume fragments, this first particle is able to hop in, and then the other particles can also follow the string-like motion. Now, this is the initial particle configuration for this string-like motion. And we consider that these free volume fragments, we call them one quasivoid, which consists of a few free volumes, and the total volume of them is comparable to that of one single particle. This is the final configuration after this string-like motion. And we can see that there are fewer free volumes because the free volumes become right here after the particle has hopped. So the conclusion is that quasivoid induces string-like motion, and also string-like motion transports the quasivoid from the string tail to the string head. Now, at this point, quasivoid may be a little bit abstract, but I think we managed to find direct evidence for its existence in a glass crystal coexisting experimental system. So this is a longer time trajectory. Again, we can break it up into 5 sub-trajectories to look at the detailed motion. At the beginning, the quasivoid is here. That is, there are some free volume fragments close by. Then by looking at the particle trajectory, we can infer the quasivoid trajectory, that it comes here and then go to the crystalline region to reach this position, which is right here. And the configuration is shown in this figure. And here, this is the crystalline region. So we can see a missing particle, and this is not a void. This is actually a vacancy in a triangular lattice. And then it diffuses around to this position, and in this configuration, we also see clearly the vacancy diffusing. And then it goes back to the to the glassy region, right here with this configuration, which becomes quasivoid again. And this quasivoid initiates string-like motion to become this configuration with another quasivoid at this position and further string-like motion. Now, so in this experiment, I think we have shown that vacancy shows the existence of quasivoid. Now, after supporting void-induced motion, then let's look at a consequence or a model motivated by that. But actually, we propose it a little bit earlier than the experimental result. Distinguishable-particle lattice model for void-induced dynamics of glass is defined on a 2D square lattice, and all the particles different, and we number them from 1 to n. This is a schematic diagram. For example, particle 9, particle 5 are arranged like this, and then that gives the configuration of the system. And they interact with a pair interaction energy V95, and particle 5 and 7 interact with energy V57. So all these VKL for particle K and L when they are nearest neighbor are random numbers sampled at the beginning of the simulation from a distribution we call G of V, which, for example, may be the uniform distribution. All these random pair interaction may be because that the particles are really different, or it may just be because of frustration. That is, the local elastic environment everywhere is different. So the interaction is different as the distance between the pair may not correspond to the bottom of the energy well, but being frustrated. When we sum up all the pair interaction energy, we get the total energy E of the system. Then we can define the dynamics. When we have a void like this, the neighboring particles can hop into the void with a rate W. And W is given by this metropolis form with depending on delta E, which is the change of the total energy of the system due to the hop. It follows detail balance. Now, if this void hop 4 times, for example, to reach this position, what's very special about this model is that the particle pairings has changed because the particles are different. And then these interactions have changed. And if there is a void close by, maybe you try to cross this path. Maybe it is impossible because some of the bond may be stable, and then it may become possible if some of the bond may be replaced by a higher energy bond, or it may be the other way around as well. So void motion affect the random potential energy landscape because of the random interaction. But reversely, void motion also perturb the PEL because the different particle arrangement. And then it affects the PEL of other void so that every void has more chances to go through a certain path, because if it doesn't go through there, it may go through this time. So this is a facilitation mechanism that promotes the motion of neighboring voids. Now, this is high temperature simulation. What we see is that the void are free to move. So it is a simple lattice gas when thermal energy can overcome the bond energy. But at very low temperature, the particle pairings like to be the stable ones. So the void cannot easily move, and these voids are trapped within one site or two sites at most. But we can see that here there is a pair of void, and they facilitate each other's motion, perturbing each other's potential energy landscape so that they can escape when the chance arises. And these two voids actually are mobile. At long time, they go through the whole plane, and of course they exchange with other voids. So the motion, the particle motions here are slow, but they are mobile, very much like in a glass. So that illustrates facilitation mechanism by this lattice model. With the model, we simulated many times to compare with glass. And today I want to talk about two more non-trivial examples. First one, Kovacs tau-effective paradox, also called expansion gap paradox. The experiment was performed a long time ago, but still considered an unsolved puzzle. Now, so Kovacs produced two polymer samples at two different temperatures, and then perform a temperature jump to the same final temperature. And look at the relaxation of the volume compared with the final equilibrium volume at long time. So he plot the fractional deviation from the equilibrium volume here against time. And look at the relaxation curve. So at long time, it would approach 0 when there was no deviation from the final volume. The down jump curve is very different from the up jump curve with an asymmetry. Now, by performing a derivative, time derivative, we can get the effective relaxation time as and plot it as a function of the deviation from the equilibrium volume. Then we see that at this point, for down jump and for up jump with a small magnitude at long time close to equilibrium, the relaxation time converges to the same value as we would expect. But for an up jump with a very low temperature from 30 to 35 degrees Celsius, it seems that even very close to the equilibrium, when the deviation is close to zero, tau effective is different from the other values. So this is the so-called expansion gap, and it is a paradox because tau effective depends on the thermal history, even when we are very close to equilibrium. Now, this is again the experimental result, and this is our lattice model simulation result by DPLM, in which we consider the energy relaxation. So we also produce up-down asymmetry, and we can take the derivative just like in the experiment. So this is the DPLM result again. Again, we see that for up jump from a very low temperature, tau effective is longer than if you would do it for down jump. And we also observe the expansion gap. So the lattice model successfully reproduces the paradox. Now, better still, we think we can explain it easily. Now, so this is a particle displacement magnitude field in the 2D lattice model. So as time progresses, for down jump, most particles more or less move somewhat, very homogeneously. For up jump, it is quite different. So many of the particles has moved a lot, completely equilibrated. But there are regions where particle has not moved at all. So further relaxation of these small regions correspond to invasion from the hot region, and they determine the further relaxation rate. But they also remember the initial condition because they have not moved, and they remember the original cold packing and the original temperature. So this is our explanation of the paradox. This small unrelaxed region dominates the dynamics, even when very close to equilibrium, when they become really tiny. But that gives rise to the history dependence as they are the initial unrelaxed region. Now we come to a second example, diffusion coefficient power loss from particle swap algorithm. Now recently, there has been much interest to add particle swap to a standard molecular dynamic simulation of glass, because that can speed up the simulations by up to 10 order of magnitude. So swapping particle is like this. We pick two particles and let them swap the position, and with a probability in the metropolis form, depending on the change of the energy of the system due to the swap. So it affects the dynamics, but it does not affect the equilibrium properties. There has been some very insightful suggestion that if we can understand swap acceleration, maybe we can understand better about glass. And there are competing theories of swap acceleration, 3 of them at least, and that either use thermodynamic or kinetic consideration to predict faster motion. But which one is correct? They are actually quite different theories. It seems we need more stringent tests of the theory if we can have more characteristic numerical features, more than just speed up. So that led us to work on particle swap algorithm. As we suggest this more controlled algorithm. So we introduce a fraction phi s of particles we call swap initiators, the red ones here. And swap initiator can swap among themselves, just like the original swap algorithm. And swap initiator can swap with regular particles, but regular particles, the blue are the regular particles, cannot swap among themselves. And we also consider only nearest neighbor swap, so that we don't have long jump. And then because we want to study a more physical system with the long jump. And we also consider swap dominating regime so that MD steps are less important. I mean, the approach is just to crank up the swap attempt rate. So these simulations are from polydispersed spheres at low temperature. Now, in this result, we show again the displacement magnitude. So these are the regular particles which has not moved, they only vibrate. These are the regular particles which has moved. And they are, nearly all of them are close by to swap initiator because the swap initiator swap with them to create the motion. And we see string-like motions, which is easy to understand because, for example, the swap initiator was here and then swap with them one by one to come to this position to create the motion in the string-like form. Quantitatively, we measure diffusion coefficient of the regular particles, dr, and plot it against the swap initiator fraction or density in a log-log plot. So we see strict lines for different temperatures. That's give the power law with exponent alpha. So the exponent alpha increases as temperature decreases because the slope increases as temperature decreases. And there is also related power law for the swap initiator, which can be easily related. So let's come back to this one. Power law are very important in statistical physics. We think these power laws are not related to criticality. It is related to facilitation, and we will talk more about that. But before that, now this is again the MD result with partial swap we just have looked at. This is different. This is lattice model result with partial swap. So we modify the algorithm so that we don't have void induced dynamic, but we consider nearest neighbor partial swap, just like in the MD. We get similar power laws. Actually, the exponents are also similar. So power laws are important for test of theories and model. And we are happy that the DPLM, our lattice model, shows the power law with the swap initiator. But it is more than that. Actually, earlier, this is simulation with the standard DPLM without swap, but with the void-induced dynamics. So we plot the diffusion coefficient of the particles against the void density rather than the swap initiator density. We get similar power laws with similar exponents. Now, the data points are from simulation. The lines are from our analytical theory, we call configuration tree theory, which is a two-parameter fit in this case for the whole data set. So the theory actually explains the power laws. And it is because of this power law related to that, so motivated us to study the partial swap algorithm. I think the similarity is not accidental. It's because actually void-induced motion, a particle hop into a void, is equivalent to the exchange between a void and a particle. So void actually is very analogous to a swap initiator. And that's why we believe, luckily, correctly, that we would have the power law here, and we should have the power law with the swap initiators as well, which we find in the MD simulations.
4 minutes left.
Oh, yeah, thank you. And and to explain the power law intuitively, at high temperature, when alpha is roughly 1, all swap initiators are mobile. So each swap initiator require each regular particle require one swap initiator to move around. So its diffusion coefficient is proportional to the density of swap initiator. At low temperature, when alpha is roughly 2, this is different, like this. When we have paired swap initiator close by to each other, because of facilitation, they perturb each other's trap, and then they are mobile. That initiate a lot of motion in the regular particles. In contrast, for the isolated swap initiators, they are trapped. So each regular particles require 2 swap initiators to move. And then we have a power 2. That's the facilitation. So that also explains intuitively the power law, just like in chemical kinetics. Let's come back to the MD simulation with partial swap at low density of swap initiators. We find that actually the motion is very much glass-like for generic glass models. We look at MSD, self-intermediate scattering function, Stokes-Einstein violation, 4-point correlation function, and string-like motion of the regular particles. They all look like generic glass models without swap. So we conclude that glassy dynamics is reproducible by defect model, and the defect can be swap initiators. Maybe it can also be reproduced by void induced motion, which we will work further on. Now, so we have introduced the lattice model. Actually, we have done a series of simulation to show that it exhibits a wide range of glassy phenomena. And we have talked about two of them, which are more non-trivial. And actually, neither of them has been reproduced by any other particle model. But DPLM reproduces quite a long list of phenomena. Now, about the analytical theory, I want to just talk about that very briefly. So basically, the void motion changes the configuration of the system, and the configuration evolution can be mapped to a graph, which is a tree. When we have a single void, when we have two void, then we have more directions to go. We have a thicker tree with more branches so that it can percolate more easily, so it becomes more mobile. That's the facilitation mechanism. And when considering that local regions can have m voids, and then we can just sum over the diffusion coefficient in this region and get a closed form expression for the diffusion coefficient, which are plotted as lines. In particular, we get the power law and also super Arrhenius diffusion coefficient, typical of glass. Now, let me conclude. We find that string-like motions dominate glassy dynamics at very low temperature or high packing fraction, corresponding to deep supercooling, most relevant for glass study. We propose quasivoid, each of which is a collection of a few free volume fragments, and a quasivoid induced string-like motion and also is transported by string-like motion. We introduce a lattice model, which reproduce a wide range of glassy phenomena, including Kovacs expansion gap paradox and diffusion coefficient power laws. So our approach has been to, based on quasivoid, look at its dynamics via lattice model and study it with analytical theory. We think it is a new and promising approach. If you are interested, please join us. There are a lot of things to work on. This is me and my collaborators, Cho Dong-Yip, Matteo Lulli, Gotham Gopini, Chen-Sing Li, and Haiyu Deng. Thank you very much.
Thank you. Thank you for very nice talk. And do you have a question or comment? Okay. Next.
Yeah, you mentioned that this technique of swapping two particles can enhance the speed of computations by an amazing, roughly 10 to the power 10. Can you give an idea how this estimate comes about? 10 to the 10 is a huge number.
Yeah. Now, this is based on Berthia's group's work. Basically, you first perform it with standard molecular dynamics, or actually they did a Monte Carlo simulation without swap, and they fit it with, for example, some typical glassy dynamics functional form, super Arrhenius form with the dynamics, extrapolate for longer time. And then they also perform the simulation with swap, and again extrapolate for a very long time. And then this speed up is from the extrapolation. So they would be able to do a simulation with swap within reasonable computation time. And then from the extrapolation, if they were to do it without swap, it will take 10 to the power 10 more time. That is maybe a century to complete the simulation. So that certainly involves extrapolation. But I think the order is quite reliable because many groups has reproduced that.
Thank you.
Yeah, thank you.
Do you have a question? Okay.
Yeah, thank you for the very interesting talk. I just have some very conceptual questions. So you showed us this lattice simulations of quasivoids, and what I think is like lattice is actually like more like crystals with defects, right? But then you are learning something about glass from these simulations. So I'm a bit confused because this doesn't look like a glass to me. So can you explain what is happening here?
Yeah, that's a very good question. Actually, using regular lattice model to study glass has a very long tradition, more than 40 years. So even though the lattice is regular, the position is regular without any off-lattice motion, but the energy is random in our model. So then now, if you have particles which are frustrated, and then you are not at the potential energy well, you will be frustrated, displaced. So the average distance between any two particles in a frustrated system is not at the well. So there is energy disorder due to positional disorder. I think there has been a lot of belief that positional disorder is not important, except that it gives rise to the energy disorder. So in most study of the lattice models in our approach or other approach, we implement the energy disorder without the positional disorder and try to reproduce glassy result. And then hopefully the result justify the assumptions.
Okay, thank you for the intriguing answer. Thank you.
Okay, thank you. Yeah, time is already done, so let's thank speaker again. Yeah.
Thank you very much.
Thank you.